Welcome, one and all, to the Cool Worlds podcast with me, your host, David Kipping. This episode, I am joined by an old friend and colleague, and that is Jason Steffen, a professor of physics at the University of Nevada in Las Vegas now. But we came up at the same time. We came up in about 2007. He was about, I think, like a year ahead of me in terms of his academic trajectory. But I remember in 2007 when I was on my PhD, the talk of the town for exoplanets was the Kepler mission, this wonderful telescope that we knew was coming next year, if everything went to plan, and it did, that was going to transform astronomy. It was going to discover not just a handful of exoplanets, which is all we really had at the time, but it was going to discover hundreds, maybe even thousands of the things. Those projections seemed so wild, one could hardly believe them. And it promised to discover Earth-sized planets. It promised to discover all sorts of exotic new things that we didn't have access to. And I remember, of course, in my own work, I was excited about the prospect of discovering exomoons with that telescope. Unfortunately, as successful as Kepler was, that was a little bit beyond its capabilities, but it kind of opened the door to doing all kinds of new, amazing work. So Jason, who is really in the mission from the early days, has written this wonderful book called Hidden in the Heavens: How the Kepler mission's quest for new planets changed how we view our own. It is a story, a personal story of his own journey with the mission, but also how the mission evolved and changed and its remarkable scientific discoveries. Things like circumbinary planets, transit timing variations, mini Neptunes, and of course all of these surprising things that we didn't really expect to find in the data but turned up. So you really need to just check out the book to learn all about that, as well as the challenges that the mission actually had during its operation as well. So in this conversation, we wanted to sort of get into this shared history that we had about the Kepler mission, talk about why Kepler was so important, what its legacy is, and ultimately, what is the future? What does it leave behind? Where are we going? Are we done after Kepler, or is there more work to be done? Spoiler alert, there is a lot more to be done. And ultimately, how can we do that? So you want to stay tuned to this episode to learn all about the future and the historical legacy of what has happened in the field of exoplanets. So please do enjoy this conversation. Jason, you've written this wonderful book, Hidden in the Heavens, and I really enjoyed reading this because it's just a deep dive for me, hearing the backstory of what's been happening with Kepler. Kepler was a big part of my career, a huge part of your own. Why don't we start by just explaining, how did you first get any involvement in this mission whatsoever? What was your origin story to the mission?
I was very fortunate to have a good advisor. And
who was that?
So my advisor was Eric Agol. He's at the University of Washington. Mm-hmm. He has a twin brother who's in mathematics at Berkeley.
Yeah. So it was weird because he's like the less well-achieving of the two twin brothers, and everyone holds Eric Agol in such incredibly high esteem in astronomy. So the idea of him being the less achieving one is just bizarre.
He has not yet won his $1 million prize for solving a
medal or something. Yeah.
They're both brothers. I met them both, but I have. It's hard for me to understate the amount of respect that I have for Eric. Is that the right word? It's hard for me to overstate. Yeah. So I have extremely high respect for Eric. I'm always grateful that he was my advisor. And he wasn't really supposed to be my advisor going in. I was expecting to work with Craig Hogan at the University of Washington doing cosmology. And
what were your interests when you first joined? Yeah. What were your scientific interests?
I had no idea.
Just figuring it out.
Yeah, I didn't know what I wanted to do. I was a physics grad student, so I went to physics departments, and I was like, well, maybe I'll do condensed matter physics, maybe I'll do astronomy, maybe I'll do whatever. I can do anything because I'll just go to a physics department that has a pretty broad footprint. And I even got into my dream school and didn't go there because my wife and I, just in discussing things, felt like the University of Washington was the place to go.
What was the dream school?
Cornell.
Okay. You'd been nearby then, yeah.
So, well, I don't know. At Cornell, I don't know what I would have worked on. They had all sorts of things that were going on in the physics department there. And the reason I wanted to go to Cornell was because my personality is one where if there's a lot of people there, then it's not as interesting for me as if there's So Cornell is like, it had the mystique, the romance of being like, oh, I know, yeah, Cornell, yeah, that's a good school, but it's not Harvard, because Harvard's a cliche
Right.
to a large
Yeah,
extent.
yeah.
No offense, but
No. It's one of those things like you're always kind of resistant to say I went to Harvard because it has a whole connotation,
yeah, there's a lot
especially
of baggage that
nowadays.
goes along
Yeah.
with it.
Right.
But
Yeah.
if you went to Cornell, it's like, oh yeah, that's a
Yeah.
good school.
Yeah. Right.
It's like
Okay.
Harvard, but
Okay. So that was the motivation for the dream, but you ended up at UW, which is
uh,
an incredible school, all the same. Yeah.
yeah, they're the two prettiest college campuses that I've
Oh, I
been to, I
agree.
think.
Yeah. Really beautiful campus. So you're working with Eric, and didn't you also spend some time at Fermilab as well?
I did. So after I graduated from the University of Washington, I went to Fermilab as a postdoc.
Okay.
It was kind of a trial run for the Brinson Fellow. So the Brinson Fellow is a fellowship sponsored by a local banker in Chicago. I mean, local Chicago means big money. And he has a foundation, and he was looking for ways to support science in the area. And so they did a test run of this Brinson Fellowship. So I was the first and the last for about a decade, but I think it's come back now where they've added the Brinson Fellowship back to the Center for Particle Astrophysics. But
And if you don't mind giving us the dates, I know it's going to age you, but it's kind of
Yeah.
important with the chronology.
So this was
of
like,
Kepler.
so I graduated in 2006. So this would have been 2006 and to 2012 that I was at Fermilab. I ended up being there for 6 years. It was 3 years was the nominal appointment time, but because while I was there, I got this Kepler grant, I kind of cut a deal with them. I was like, hey, if I'll pay half my salary, if you'll pay half my salary. And so that stretched it out for 6, which is good because academic life is not built for families.
Yeah.
And by then
That
I had,
flexibility helped. Yeah.
I had all three of my kids by the time I left Fermilab. And so it helped us because we could stay in our house the whole time.
Right. So just to rewind a little bit, that's your postdoc was at Fermilab, your graduate student you're at UW, where Eric was your advisor, and that's how you got connected to Kepler. So maybe just explain that a little bit more.
Yeah. So with Eric, my original goal or the original idea that for my dissertation would be to do the imaging of the galactic center black hole using VLBI, very long baseline interferometry. So the images of the black hole,
Like the EHT.
yeah, that came
images,
out.
yeah.
That was what my dissertation was supposed to be, was doing the calculations to predict what it would look like. And I thought it was the coolest thing ever. But
It really is. Yeah. I mean, those images were mind blowing. Yeah.
just the amount of work that it takes to,
Right.
all the things you have to account for in order to turn the whole Earth into a telescope is pretty mind boggling. So that was what it was supposed to be, but I hadn't had general relativity yet. And so Eric thought, well, we'll just do this practice problem because it's kind of classical mechanics. And then when we're done 6 months from now, we can go back to the real problem. And so the practice problem was looking at the dynamics of planetary systems and seeing how you could measure the changes in the orbital period because of the planetary interactions and how that would show up in the transits of the planets in front of the star. So a planet, when it passes in front of the star gets a little bit dimmer, and you can measure really precisely the time that those transits occur. And if there's a second planet in the system, then as those planets interact with each other, the orbits change slightly, and you can see those slight deviations in the orbital periods.
So that if an alien watched from the Earth should see, if the alignment was right, they would see the Earth transit the sun once every 365 and a quarter days, but the influence of the other planets will slightly change that timing.
Yeah, so Jupiter changes it by probably a handful of seconds, a couple dozen seconds.
Right.
Venus
So when we
changes it by a
celebrate
little bit.
January 1st, New Year's Day, we should really be doing the calculation to see exactly
when it
Jupiter's
is.
doing.
Well, and in fact, because some of these systems, if you have planets that are really strongly interacting because they happen to lie near what's called a mean motion resonance. So when you have a system where every 2 times one planet goes around, the other one goes around once, or every 3 times one goes around, the other one goes around twice. When you have those kinds of commensurabilities, the deviations can become quite strong because they add coherently from one to the next. It just
Right.
keeps building over time.
Yeah, so that means that the point of closest approach between the two is at the same point in space over and over again. So that interaction is just warping those orbits
orbit.
at the same place.
Yeah.
So it's like scratching an itch almost at the same point.
It's the same thing with like if you push someone on a swing and you do it at the right time,
Yeah.
relative to how rapidly they oscillate. If you're pushing them at the right frequency, then you can get the deviations to be quite large. And so when you can have, as we found with Kepler, when you have some planets, they can interact very strongly to where it would be the equivalent of once a decade, you lose a month in the year, and then a decade later, you gain another month. So there's 11 months in 1 year, and then 5 years later, there's 13 months.
That's like Game of Thrones, right?
Yeah. So it's even, then like celebrating your birthday would be even harder. You would have to say like, okay, where's the star? Where are the stars in the sky? And that's when your birthday is.
So was this idea present at that point? Because it does seem, in retrospect, that you wrote this paper with, well, a few papers during your thesis. And I think in 2005, there was this really seminal paper that your advisor led, Eric Hagel. I think you were second author on that paper.
Yeah, I was second author, and then Rem Sari, who's now
in Clarkson, I think was the last one. And then there was also the Holman and Murray paper, which came out completely independently the same year, 2005. And these two papers, for me, were like the eye-opening papers that transit timing variations is a big deal and it's here to play. Was there before those papers came out, obviously Eric had this idea, but was it already literature? Were people thinking about this before?
So there were papers. I don't know that it was congealed into a literature yet. They were kind of independent ideas, and it hadn't solidified in terms of, when I think of a literature, it's like, there's a whole series of papers that are all kind of referencing each other.
There was no review articles at this point. Yeah.
And so the one that we knew about, I guess there were two that were really relevant. One of them was a Borkovits paper that was looking at the same effect, but it was using stellar triples. And so we used his work to kind of as inspiration for some of the cases that we studied. And then there was another one by Jordi Moralda Escude.
Oh, yeah.
And
was that a precession?
I don't remember the details of his paper, but and then apparently there were some others that we didn't even know about, but those two we did know about.
Yeah.
And so we pointed out some of the differences, and it turns out that actually Jordi was our referee on that paper. And so we were like, in our paper, we said, there's these differences and we don't totally know where they come from. And then the referee's like, oh, I'm that guy, and here's actually where they come from. So he, kind of.
Okay. So that when this paper came out, was the idea that the paper came out and then the Kepler team got on the phone to you guys and were like, we need you to help us out? Or was there already involvement before then?
So it was really fortuitous, because with pretty much every NASA mission that I've seen, especially every NASA mission that's led by a PI, principal investigator, they will do a search for participating scientists, mainly because the people that build the spacecraft aren't necessarily the scientists that are going to use the data. You don't want me bolting together a telescope. You want like real spacecraft engineers, aerospace engineers to bolt together the telescope. And so the team that you have when you're building the mission is different than the team that you want to have when you're collecting data and analyzing the data. And so the way NASA addresses this is that when a mission's about ready to launch, they send out a solicitation for participating scientists to join the mission. And then they come on with the kind of express purpose to do the science to spread out. 'Cause you have a few scientists that are on there to advise the mission in the design, but then when you actually start collecting data, you want a broad range of scientists who can all use the data. And so it's standard practice for NASA to solicit participating scientists to join the mission. So that solicitation came out right after I graduated, and one of the lines,
2006.
Yeah, so it came out, I think, 2007. It probably came out in February 2007. So
the mission launched the next year, 2008.
It was supposed to launch the next year, launched 2 years later.
Okay.
So I'm thinking, I'd have to go back and look at the dates directly, but I'm thinking that they came out in the solicitation that comes out in February every year.
Right.
Except this year. So it would have been February 2007. So it was really less than a year after I had graduated. And one of the things that they explicitly said, we're looking for scientists who can do the following things, or science similar to the following things. And one of the things that was on that list was looking at for additional planets by studying the variations in transit epochs, which is basically it was almost the title of my dissertation.
Perfect.
And at the time, while there were a number of groups who were working on it, at the time I was the only person who had published those kind of analyses. So Fermilab was gracious enough to let me apply for it as a principal investigator, because a lot of universities don't allow postdocs to serve in that capacity, but Fermilab does. And so had I not gone to Fermilab, I wouldn't have been able to join Kepler.
Which is weird to think, because you think Fermilab, you think particle accelerator, what's that possibly got to do with looking for planets? And somehow that ended up being the perfect match.
When I got the job at Fermilab, I asked, after I said yes, and they said, okay, we'll send the paperwork over. I said, can I ask a question? This was Rocky Cobb, the pretty famous cosmologist. He said, yeah, go ahead and ask. And I said, why did I get this job? And he said, well, you had very good letters. And I'd done some work in neutrinos. I'd done some work in gravitation experiment. And then this work in exoplanets.
No, I'm not surprised you got the job. You're extremely diverse in your interests, so it makes total sense that on your journey you'd spend time at Fermilab. It's just a very Jason type thing to do.
So I loved it at Fermilab. It was a really incredible environment to participate in. Fermilab is so hardcore in you don't talk about things other than science, really. Before I got there, they used to have notepads on the tables in the cafeteria so that people could sit there and work out, let's think about this kind of thing, and, design new things or talk about the issues that they're confronting. It was all science all the time.
Yeah, that's awesome.
And so it was really an incredible environment to be around. And then after I left Fermilab, Fermilab let me submit a proposal where I could be the principal investigator, which is what you have to be in order to serve as a participating scientist. And so I was accepted. Myself and Matt Holman at CFA were both accepted as participating scientists, kind of to do the same research. We had slightly different proposals, but they essentially were the same.
Did that create a sense of competition or collaboration? How did that work between you?
I think
especially because he's more senior than you.
Yeah, I think it could have turned into an issue. But one of the things that happened fairly quickly with me is that I became a co-chair for the multi-body working group. So I was like the TTV working group chair, and then Jack Lissauer was the multi-body working group chair, and
so much more like multi-planet systems.
Yeah, so anything that related to multiple planets in a system, the dynamics of multiple planets, and so Jack and I, we basically just merged the group together, and we would switch off from one week to the next. Who effectively was running the show, but I felt that it was really important to have a good collaborative environment where people could air what they wanted to work on. I remember one instance where there were a number of people that we were brought into one of our telecons who were working in RV, like Doppler shift type things. And, they had what they wanted to work on, and they had their students that they wanted to do something with. And we also had our things, and nobody wanted to speak up because, we were all friendly with each other, but now we were really, in a situation where we could step on each other's toes and things could go south. And for better or worse, I just said, speaking to one person, why don't you tell us what you want? Like, what is it that you want to work on? And we'll have this person say what they want to work on, and we'll have this other person say what they want to work on. So we can even see, is there overlap? How much manipulation do we need to make in the scope of the different projects so that everybody has kind of a shot?
Yeah, I definitely get that tension, because obviously I wasn't in the Kepler mission, but I almost became part of the Kepler mission at one point. And I remember being told by someone senior in the mission, I won't say who, that if you join the Kepler mission, you'll be working probably for Jack Lissauer. Mm-hmm. And if you find an exomoon, which is what I was interested in doing, you will not be the first author on it. That's not going to happen. I don't know if that person was misinformed, but that's what they told me. And I was like, man, like that, they were like, someone's already doing that in Kepler, so you can't come in now at this point and take over exomoons. That's already been decided who's doing that. So it did seem like the pie was being cut at an early point in the history of Kepler.
Yeah, that was true. We definitely had people saying, okay, these are the systems I want to work on. A lot of those things never came to fruition. There was way more things to work on.
Right.
I'm not convinced that someone would have supplanted your authorship, but
Yeah, I think in hindsight, there's a lot of stuff that people predicted at the time that is not how it ended up at all.
yeah,
Right? Yeah.
there was a lot of things that we were reticent about in like how the mission operated that turned out to not be necessary. At the time, there were good justifications for it, and I don't know that we would have made a different decision.
So what's an example of that?
Like the data releases. So how frequently we release the data to the public. It was originally supposed to be that we would release with each successive data release, which was supposed to be on like a yearly calendar, we would release half of the data. Because with half the data, half the data gives you the orbital periods out to a given duration. And
So you need normally 3 dips to confirm the planet, but even 2, I guess, is just about enough to.
it's enough. Well, it's enough to say that there's a planet there, but you don't know if you missed a transit.
Right.
And so there's an ambiguity that you solve or you resolve when you measure the third transit.
So if you're an alien watching the Earth, you'd need at the bare minimum 365 days of data, but that's assuming you're extremely lucky and you caught one right at the beginning, one right at the end. So in practice, that the amount of data you're releasing sets a window as to what is discoverable.
Right.
Yeah.
And so for the first year and a half, 2 years, that was the schedule that we adhered to. But we realized that the fire hose was blasting data so fast that there was just no reason, there was no need to keep the data kind of proprietary for as long as we thought. So after a couple of years, we just went with, we're just going to release all the data all at once. And so that actually formed the TESS approach. So the TESS mission, that's a successor to Kepler, a lot of the things that they're doing with how they release their data came from specific, with the TESS, there was a meeting in Boston that we had, it would have been 2011, I think. And that basically was what determined how the TESS.
So TESS just dump all the data as soon as they get it.
As soon as they can,
much.
yeah.
Whereas Kepler was, we need 1 year to
release
for the team
things
to
out
look
to
at
6
this
months.
first.
Yeah, to release a planet candidate that had a 6-month orbital period.
Okay. Yeah.
And it was that meeting where it was decided, and there was an argument, which is not a bad thing to have arguments about some of these things. So people are heard, right? Like everybody gets their voice out, everybody hears, and then there's a decision made. And maybe you disagree with the decision, but as long as you've made your case. So it was decided at that meeting that we would stop doing the half the data thing and just go with, when there's new data that comes out, we'll release it as soon as we can get it processed. And that was also, that's the test model, basically.
So that happened midway through the Kepler mission.
Yeah, it was about 2 years in. So
okay. Yeah, because I remember at the time, there was a huge advantage to being a part of the team because you had access to the proprietary data, and I was obviously on the outside. And I remember thinking to myself, well, in 1 year, that data is going to be released. So maybe is someone really going to find an exomoon in a year? Like, I feel like it's a lot of work to pull that off, and I've probably got an advantage, and I've built up these models and stuff. So I think I remember consciously thinking, I'm just going to wait it out, and because I can't look for a moon around an object unless it's been a confirmed planet. The planet has to be confirmed first. Let the Kepler team confirm the planets, and then when you guys confirm the planets, I think the other mandate was any published papers, the data also had to be released with those papers, right? So it seemed to me, I was kind of weighing like, okay, these two options of maybe not get the credit for doing this search, plus the fact the data is probably going to come eventually anyway. I remember thinking consciously, I'm going to just risk it. I'm just going to wait for the data. But I remember you mentioned in the book there was this 6-month delay, right? So that was, the schedule was shifted. Was that the first data release?
So yeah, the first data release was supposed to come out, I believe this was 2010. I wrote it in the book so that I don't have to remember the year exactly. I believe it was 2010 it was supposed to come out. And one of the concerns that we had, because up to that point, there had been a lot of retractions in exoplanets. And so we didn't want to release a bunch of data, have people make claims of what they could find in the data, and then those claims would later be retracted, and then those claims would later be retracted, and we would be the ones who suffered the fallout from, oh, well, Kepler, claimed to do this when it wasn't actually the Kepler mission that claimed to do anything. And so we weren't prepared to do the analysis of the smallest targets or the smallest signals. And so I actually helped draft the request to headquarters to sequester 400 targets from the data release, so that we could have
keeping
time.
those top secret, basically.
Keeping them proprietary until the subsequent data release. And the reason was that we still have a bunch of analysis, tweaking the analysis pipeline, making sure that the code is working the way that we want it to. And we just found out that some stars do this thing, and we need to account for that. And we just found out that what turned out to be paint chips drifting across the field of view will brighten the whole telescope and make it so that we can see spurious signals that aren't real. So because of that, it wasn't really ready for the really small things, because there were systematic effects that were comparable in size to the signal we were looking for.
Right.
So we requested a period of time where we could finish up the analysis of those ones before they were released to the public. And I drafted, it was basically me and Bill Barucki. I think I did most of the text, and then he went through and cleaned it up. He gave me an outline, but it's been a while, so it's hard to remember exactly how it worked out.
This obviously it was a little bit of a dangerous move in a sense, because there's always conspiracy theorists out there.
Oh, and they came from everywhere.
Yeah, and especially because you mentioned that there was this talk that Dimitar Sasilo gave. There was a TED talk, and this was just prior to the data release, I think, or around the time of the release, and he mentioned you guys had a bunch of Earth-like candidates that you were looking at. Am I saying that right?
As I recall, because I did rewatch it when I wrote the book, as I recall, it was basically him estimating how many there would be given the performance of the spacecraft.
Okay.
So it's like, the way that the spacecraft's offering, we should be able to see, a few dozen candidates.
So people saw that TED talk and thought and then saw that you were hiding the data for another year, 6 months, and got very anxious about that.
It was pretty gnarly. And a lot of people were up in arms. There were a few people in the exoplanet community more broadly who were disappointed. It turned out that, 8 months late, it ended up being 8 months later that those data came out, and people weren't ready for it then either. So it didn't really matter. And it was a flash in the pan. I mean, you have to find news where you can find it, I guess.
Yeah.
So I don't necessarily blame a reporter for covering that. I will say that there were people who really distrust NASA, and they were asking for all the emails. I want every email that's related to this thing that has to do. And so there were a couple dozen NASA employees who wasted a huge amount of time where they should have been working on the Kepler pipeline in order to get the data processed, but they went back looking through their emails to comply with a FOIA request. I'm kind of a fan of proprietary periods to give people a chance to chew on the data. If you've built something and you take the data, I think it's perfectly fine for someone to listen, especially coming from experimental physics, where I led a search for one of a dark energy particle. And it was me and my team who built the instrument.
A dark energy particle or dark matter?
Yeah, dark energy particle. So it's called the chameleon dark energy. That Amanda Weltman and Justin Curry, they were the ones who wrote the paper about. It's basically how do you have a scalar field that evades the torsion pendulum experiments? Because torsion pendulum experiments, once dark energy was discovered, if it's due to a scalar field, which is a pretty typical extension to the standard model, we'll add a new particle, it's just a scalar, and it's going to have certain properties.
So by scalar, you mean it acts the same everywhere, basically?
Yeah, temperature is a scalar field. It's just a point in space has a value, and it doesn't have a direction. Where an electric field has a direction, but a temperature field doesn't have a direction. So it's a field that exists in the universe, and the properties of that field that would give you dark energy. And so as soon as that was proposed as to explain the supernova data from the late 1990s, there was a group at the University of Washington who were like, oh, we can build something to look for these kinds of particles. And so they built it, and they didn't see anything. And so then 5 years later, the theorists in cosmology have to come up with a way to still get the effects of a scalar field without having it actually be a scalar field in a laboratory setting, or without having it behave like a scalar field in a laboratory setting, meaning that you can evade the torsion pendulum experiments based on the properties of that experiment. So the chameleon particle was one of the particles, or one of the candidates that came out of that, I guess, theoretical exercise.
Yeah.
And so the team that I led, we built this experiment. We designed how we're going to do it, how we're going to run it. And so after we were done, it's not like we're just going to be like, okay, now we're going to release the data to the public and let someone else do the analysis. The whole point of building the experiment was to be able to also analyze the data. So we had people on the team whose job it was to do the analysis. So in astronomy, like, particle physics has a much more healthy relationship between the people who bolt things together and the people who analyze the data in the end. Most astronomy papers don't credit the telescope designer, even though they're dependent on the telescope designer. So maybe particle physics goes too far, but it's the other direction.
Yeah.
Right?
So when Kepler was first starting, there was a lot of different expectations about what it would be able to achieve, and it kind of blew some of those expectations out the water, and others maybe didn't quite fully realize. What were the things that I guess you were focused on transit timing variations, these wobbling planets. What did you looking into a crystal ball, but retrospectively back then, what were you expecting Kepler to deliver for TTVs? Did you think we would find, because I'm like the Holman paper we talked about earlier, I think the title was something about being able to detect terrestrial mass planets from TTVs. And I still think even today, there's no example of a non-transiting terrestrial mass planet that has been found through this method. So there's some things which it expected to find, but were not delivered. But then there's all sorts of stuff TTVs have done we didn't expect. So what were your sort of...
Well, so at the time, there was still an issue that we didn't know where hot Jupiters came from. And so the main competing theories were that there was eccentric migration. However, that eccentricity, so eccentric migration meaning that you have a Jupiter, you excite its orbit into a highly eccentric orbit, which brings it close to the host star. And then over time, the orbit will circularize near the pericenter, near the close approach to the star. So eccentric migration was one avenue to produce hot Jupiters. The other avenue was that they were embedded in a disk and then they migrated inward because of drag with the gas. If the disk migration was common, then you should expect to find terrestrial mass planets trapped in these mean motion resonant orbits. The same kind of thing happens in the solar system. So Neptune and Pluto are in a mean motion resonance because Neptune migrated outwards into a disk of small objects and captured them into these orbits. And the same thing would have happened in these planetary systems.
So you'd have you'd have the hot Jupiter really close to the star, and then external to that, you'd have a 2-to-1 or a 3-to-1
right.
Earth, basically.
And they could be ones that, because Jupiter mass planets migrate differently in a disk than terrestrial mass planets do. A Jupiter mass planet opens up a gap. It migrates much more slowly, where terrestrial mass planets, they basically just see a headwind and they migrate quickly. And so if you have outer Earth-like planets, they will migrate faster than the Jupiter and capture into external mean motion resonances. Or you can have the Jupiter migrating inwards and it will shepherd inner Earth mass planets into the same kinds of orbits. So it's a slightly different mechanism, but it results in the same thing, that you can have terrestrial planets in mean motion resonance with the hot Jupiter. So at the time that Kepler launched, that was still a completely viable theory. And we know now that it actually works in some circumstances. It's not the most common method or mechanism to form hot Jupiters, but it is a mechanism that does form hot Jupiters.
Because hot Jupiters are notoriously lonely.
Yeah.
Right? They very rarely have any planets around them. We now know, but I guess when Kepler launched, we didn't know that was true.
Yeah, so we knew that they didn't have any nearby large companions. we knew that there were a few instances where you'd have a hot Jupiter and a distant secondary Jupiter. But at the time that Kepler launched, those were fairly rare, and there was a theory that predicted that there should be terrestrial mass planets in mean motion resonance or near mean motion resonance. So when Kepler came along, that was the best data to do this kind of analysis, and I was able to lead a paper where we didn't see anything. We didn't see anything that stood out. A few years after that paper, there was one planet that was found that had these telltale terrestrial mass planets that would indicate that there was disk migration that took place. But that didn't happen until the K2 mission launched.
Even if you had a hot Jupiter, that Kepler had found a whole bunch of these things that had TTVs, would you still need to detect the terrestrial planet in transit, or was the idea that you would be able to infer its presence solely based off the wobbles of the hot Jupiter?
It helps if you can see it in transit, but it's not necessary. So they were sensitive enough, Kepler was easily sensitive enough to see Earth mass planets, provided that they were in these orbits where this transit timing variation signal is amplified. Because even before then, there were data that were capable of detecting Earth mass planets, but because they're so rare, they don't show up. It turns out that it's a few percent of hot Jupiters that have terrestrial mass planets in these mean motion resonances. And I suspect that that's actually due to a separate population, that you have Jupiters that form in general, and they migrate in disks in a variety of ways, and the tail of that distribution produces some fraction of what we would call hot Jupiters with these terrestrial mass planets. And by the same token, you have eccentric migration that produces a much larger ensemble of Jupiter mass planets in 3-day orbits.
We'll be right back after this short message. This episode is brought to you by our sponsor, NordVPN, my personal VPN of choice for the last few years now. So I'm sure you know this already, but VPNs add a vital extra layer of protection when you're online, redirecting traffic through proxies which mask your IP address. Especially when you're using public Wi-Fi's like at coffee shops and airports, this has become an essential tool for me and my family. NordVPN has over 5,800 servers in over 60 countries worldwide, so you can make it look like you're just about anywhere. So a neat side benefit of this is that you can actually stream TV shows that are only available in certain regions. And trust me, NordVPN is plenty fast enough for this. I love it because the app is clean and simple, and it works on everything from your phone to your smart TV. So we've partnered with NordVPN to give you the best deal out there. When you use my link, you will get a huge discount on their 2-year plan, plus 4 additional bonus months. So get it at nordvpn.com/coolworldspodcast. It's risk-free with Nord's 30-day money-back guarantee, and it is the best deal on the internet. Once again, that's nordvpn.com/coolworldspodcast, or click the link in the show notes. Now back to the episode. So that's one thing you can use TTVs for. Obviously, there's circumbinary planets that we've discovered with Kepler. There's exomoons, which I've been looking for. There's Trojans, which you mentioned briefly in the book, things like this. So were all of those other ideas sort of just science fiction at that time? You just thought the hot Jupiters is the most likely thing we're going to get data from?
I'll say that we weren't surprised when we saw the first TTVs, but we were gratified. So it's like, these should be there. We should see them. And when you do see them, it's like, okay, there it is.
Yeah.
So
the first one was Kepler 9, I guess.
Kepler 9 was the first one. It was the first one that we did a paper on because
it was so clean.
Yeah, it was pretty clean. There were others that showed TTVs. In fact, some of them that early on were like, oh, we definitely got to do this one. We definitely got to do this one. And then there were just so many to study that some of them still have not been studied to even today, like 15 years later.
Yeah.
So that just goes to show that there was so much data from Kepler that we really didn't have that much to worry about in terms of, is there going to be stuff for us to do if we release this to the public? There's so much stuff still to do in the Kepler data that hasn't been done.
Yeah. I mean, I kind of feel that way today we had the Rubin's first light celebration today. That's the day we're recording this on, June 23rd. And the sense of how much data is going to come from that, it reminded me a little bit of the early days of Kepler. They're talking about 20 terabytes, which is obviously way more than what Kepler had, 20 terabytes per night of data. And I'm just thinking, how are we ever going to, we're going to be years and years catching up on that, even like a couple of nights of data from that thing.
Well, it reminds me a little bit of like oil exploration.
Yeah.
That when the oil peaks, oil production peaks when you discover half of the oil, because then it falls off the other side. So the peak productivity is when you're getting half of the information out of the data. Because you literally are kind of extracting information from the data. And so when you get to the halfway point, then it's harder and harder to pull things out. Yeah. I mean, that's my working model. I don't know if it's actually
like the
true.
Pareto rule that you spend 80% of your time dealing with that last 20%, right? It gets harder and harder. So, and a lot of actually young people often ask, Josh Wynn sometimes talks about this in conversation with me. I was like hearing his thoughts. He gave a talk once and he said, young people ask often whether the golden age of exoplanets has passed. Whether, because certainly when I was starting out and you were starting out, we were only a year different in terms of our PhD. I had this sense that this was like a massive boom area, right? There was just, Kepler was going to find thousands of planets, and at the time before Kepler launched, there was only a few dozen or so. So it just seemed like there was going to be this explosion. Do you think if you're a young person entering the field now, you might choose a different path, and rather than entering exoplanets, you'd be drawn towards the imaging stuff that you're originally supposed to do?
So if I were to go into astronomy today, what would I go into? I think exoplanets is still fruitful. One issue is that the easy stuff has been done. So I don't know that you can make a career out of doing what I made my career out of. It has to be something else, because there's already people now that have the faculty were selected from among that group already. And so it's incumbent upon, well, advisors like myself to try to find innovative areas where, for those students that we have that want to continue in academia, where they can make a name for themselves that hasn't, like, they can trod new ground.
So you think we're past that halfway point in the oil analogy?
I think that there's a lot to do, but it requires a lot more background information. So especially since once we were capable of detecting interstellar asteroids, we found one. It was within a decade from the time that we were able to see an asteroid that came from out of the solar system where we found one, which means that these things must be, either we're the most lucky people ever to exist in the history of the universe, or it's common to have exo-asteroids come through the solar system. So I think there's going to be new data, new kinds of data that come out, but really understanding the implications of those data is going to require a different base of knowledge than kind of probably a bit more expansive. For one thing, there has to be a bit better communication between exoplanets and planetary scientists. The planetary scientists, they study things in the solar system, and they get a lot of information from things that most exoplanet people just don't they don't know, because they're not exposed to it. It's not part of the bailiwick of things that we look at. So I think that there's a lot of promising ground in that area. There's going to be new instruments that come online, and being prepared to use those instruments, like the Roman telescope and the whatever concepts are still being developed, Habitable Worlds Observatory, things like that.
Imagery, yeah.
I think there's quite a bit of technology that's going to come out in the direct imaging side. It's not ready for prime time yet, in terms of you're not going to see Earth-like planets in the habitable zone yet. There's still another generation away, but I think some of those issues are going to get resolved. And so there's going to be more information, like different kinds of data that are going to come out. So that's going to be, I was extremely fortunate to happen to work on a project where the technology to use what I worked on became available right after I had done the theory behind it. And I don't think that's I don't think that's really common. Certainly not backing into it the way that I did. But that doesn't mean that those opportunities aren't there. So it's up to advisors and their students to keep their eye out for, hey, what are the things that are coming down the pipeline? What can we do with those data once they come down?
Yeah, I agree. I mean, that's why in my team recently, we've been really excited about planetary ablateness. I think a lot of people are getting interested in that because that was something that was just out of reach of Kepler. Couldn't really measure that. So this is the idea that a planet, as we all know, like Saturn is wider at its equator than it is at its poles. It's about 10% wider. So that will cause a measurable anomaly in the data that we can look for. I don't think people tried too hard to look for it in Kepler just because it was an expectation it would be just a bit too difficult to see.
There was discussion about stellar oblateness, trying to see
Yeah.
stellar oblateness, and what does it look like to transit across. So when stars rotate really quickly, they flatten out like an M&M, and a consequence of that is that the equator is cooler than the poles. And so
you get this kind of gravity darkening effect. Yes, yeah.
And so if you transit across that, then the transit light curve is a weird shape because you're transiting a darker portion of the star. And so that was something that was discussed.
That's pretty exotic though, because it's pretty rare a star is. I'm thinking like Kepler 13, I think was one of those, or KY. I think KY 13 and Kepler 30 is the same thing. It was one of those rare cases where the Kepler internal number is the same as the public number, but that had this very weird asymmetric thing going on.
And part of that was by design because the Kepler mission was specifically targeting F, G, and K stars, and then M stars were added on kind of later. And the really fast rotating stars are more massive stars that wasn't really in what the Kepler wanted to target.
Yeah, so that makes sense. But yeah, I totally agree that it's if you're going to do an occurrence rate paper now, there's been probably 100 Kepler occurrence rate papers published, I reckon, at this point. And you can publish it. And part of me wants to do that kind of work because you can look at that literature and you think every single one of those papers, oh, there's something I'd do different there. There's something I could improve just slightly. So there is always a temptation to have that kind of masterpiece syndrome of wanting to like improve everything that's come before. But if you're the 101st paper,
the 111st,
yeah, however you say it, it's really hard to stand out. Whereas if you look at the very first occurrence rate paper I remember was by Andrew Howard, and it was only
a bazillion citations.
Yeah, it's a huge number of citations, a massive impact. I think it was published in Science or Nature, but it was only out to, I think, 50 days, 50 days orbiter period as far as they went. And the methods are extremely outdated compared to what people use today. But even just being first sometimes is 90% of the game in science, unfortunately. So yeah, it is getting difficult to make a big impact. And obviously Kepler had many of those firsts. And we mentioned a few of them, like circumbinary planets. I remember for me, that was the one, I think it was Extreme Solar Systems Conference, and Josh Carter presented, what was the name? Was it Kepler 16? I think was the name of the system.
Kepler 36.
I think Kepler 36 is the 6 to 7.
Oh yeah, right.
That's another Josh Carter one though. But I think the first circumbinary planet, the Tatooine,
16, yeah.
I think was 16.
So Lawrence Doyle is the person who led the study.
Okay, and then maybe Josh was.
But I think Josh probably did.
Yeah. I think he gave the talk. I think Josh gave the talk. But I just remember that being like, wow, we're living in the future, right? Seeing a circumbinary planet. Was there a moment like that? Do you remember a particular favorite discovery where you saw it for the first time and it just blew you away?
There were a lot of, so certainly the circumbinary planets, first TTVs. I think the architectures paper, seeing the different period ratios where there were excess planets.
So maybe explain what that was.
So the architectures paper was, okay, let's take a look at all of the systems, all the planetary systems that Kepler found, and see if there's any interesting things that we can infer from the collection of all of them. So
demographics, essentially.
So how do the planets relate to each other? What's a typical relationship between planets in a single planetary system? And so that's the architectures. How are systems built? How far apart are the planets? How do their orbits relate to each other? Because part of the reason we want to study that is because that gives us information about the histories of the planetary systems. If you see certain behavior if you see certain types of orbits and certain relationships between the orbits, then that tells you that the planets moved around, and it tells you which direction they moved, and so there's a lot of history that you can get from that kind of information. What fraction of the time do planets migrate towards the star, and when they do, what fraction of the time do they have other companion planets nearby? And then how does that compare to the solar system is kind of, because the solar system is obviously the baseline for a lot of exoplanet science, not all of it, but a lot of exoplanet science is really looking for, are there solar system analogs? And if we have planetary systems that aren't analogs to the solar system, then what's the difference? How is their history different than the solar system history? So I think that was a big kind of
when you saw
groundbreaking
that
thing.
plot for the first
Yeah,
time.
when we see those kinds of variations.
And there is a surprise in that diagram, right? I'm thinking of the excesses outside of resonances. Is this the same diagram you're thinking of?
So there's a lot of excesses outside of resonances, and then there was a big lack, or like a dip in the frequency of planets that were inside of the resonances.
Okay, so if you look at a 2-to-1 resonance, you see in the solar system you have Io, Europa, Ganymede. They share this 2-to-1, 2-to-1, 2-to-1 on the outside. So that seems like from the solar system that's something that nature likes to do, and we have good dynamical reasons to think that's a stable, favored thing for planets to end up in. And yet when you look at this demographics information, you see not exactly the opposite of that, but you see a deficit. You see fewer planets there than you would expect, not zero, but fewer. And then just outside of it, so like 2.1 to 1 or something, or 2.05 to 1, that's where you get the spike.
Right.
That's really weird.
And so it's broken, like the resonances are broken.
Yeah.
And so there's some mechanism to break them.
To push them out of that gravitational well, almost, out of that point of stability, yeah.
And so there were a handful of papers that came out trying to explain the origin of that. So that was, I think, one of the big discoveries. I will say that some of the things that I really liked, maybe it's just because I worked on it, and so then I cared about it more than other things.
Yeah, that's what I want to hit. The personal story is the more interesting one.
But I haven't had a lot of success at getting other people to care about them. So one of the things I think is really interesting is the hot Earths. So and I'm going to follow your example on this, or I want to follow your example on this. I think that exoplanets, as an ensemble, we scientists are mislabeling some of the planets that are out there. So for historical reasons, there are these things called ultra short period planets, and that are planets with orbital periods less than 1 day. The historical reasoning was that was where Kepler stopped looking for planets. So the Kepler pipeline would look for planets with orbital periods of basically 1 day and longer, and they didn't bother with looking at orbital periods less than 1 day. Yeah, because why would we look for something with a 3-hour period? I mean, why would anybody do this? There's no reason to expect it to exist there. And so then Josh Wynn, Saul Rappaport, and
Roberto Sanchez, I think. Yeah.
They were like, well, here's a thing that the Kepler team's not doing, so let's look at it. And so they naturally said, okay, we're going to look for things with less than 1 day orbital period. And so that became the de facto dividing line between ultra short period planets and then just regular planets. But if you look at the demographics of where is there a bunch of planets that all have similar properties, the 1 day threshold goes right through the middle of the population of hot super Earths or hot Earths. And so it's like the worst possible location to place the definition of ultra short period planets, because you want to capture, when you make a new term, these are ultra short period planets, you want to capture all the planets that have the same dynamical history, the same formation pathway that produce these planets. You want to have them all together.
Yeah, it's a physical group, not just a arbitrary
historical artifact group,
yeah,
right?
Yeah.
And so so that's an area where studying these hot super Earths. So so I call them all ultra short period planets or hot super Earths. I usually steer away from the ultra short period planets because people immediately think of the 1 day cutoff, which I understand where it's coming from, but I'm like, please let's use the right names for these things.
The story reminds me a little bit of a story I heard. I don't know if this is true or not. Maybe is that with the very first discovery, 51
55
Peg.
Cancri E.
No.
Oh,
Pegasus.
51 Pegasus. Yeah.
51 Pegasus VB. There was, that was a very short, surprisingly short period at the time, like 3 days, which is now like a classic period for a hot Jupiter to have. And then I think the story was that Jeff Marcy and Paul Butler had all of this data they'd taken, but they hadn't searched for periods below some certain limit. So that 3-day periods they had never even thought to consider were possible for the sake, like, how could you have a 3-day period planet? But didn't even search for it. And then they, once they heard the announcement, they ran through the archive, did the periodogram just a little bit further down. And what do you know? They found like 3 planets in one day. And then I think they published 3 planets within the space of like a couple of weeks of that first discovery or something crazy.
So I seem to recall, and I missed part of the conversation, but I seem to recall a conversation at this Jackson meeting, the Extreme Solar Systems that was held in Jackson Hole.
I was there, yeah.
And Jeff was telling the story. He was like, and Michel Mayor called me up. Was like, "There's this thing, and I don't understand." And I'm wondering if that's related to the same instance where it's like, "Oh, I should look at that too."
Yeah.
But it also, a similar thing happened with hot Jupiters because back in 2005, so 20 years ago, a hot Jupiter was basically anything that wasn't on a decade-long orbit. So you have a hot Jupiter with a 40-day orbital period, and now we don't consider those things as hot Jupiters.
Cool
Yeah,
Jupiters.
those are. And so, a similar, once you identify, oh, here's this population, they have this shared history in how they form. They all are going to have orbital periods within some window. That's when the term actually means something physical. There's a lot of baggage that goes along with that. That's not just arbitrary choices by someone on the Kepler team to say, well, 1 day is probably a good enough place to cut it off. So I think the ultra short period planets, so these hot Earths, the 1 day, they center at 1 day, like 1 to 2 day orbital period Earth-like planets. Those, I think we should want to understand where those come from, because they are, for Kepler 10, for example, is a 20-hour orbital period, and it has a companion. The companion has an orbital period of like 45 days. 1 day to 45 days, that's a 45 to 1 period ratio. That is an enormous gap. Dynamically speaking, that is a huge gap. That would be like having Mercury and Neptune as the only planets in the solar system. And like, how do you get planets that are this widely separated, dynamically speaking? If they were, 3 to 2 or...
and also, what's wrong with all of that middle ground in between? Like, why wouldn't that form planets?
How do you drive these? How do you get this planet to detach itself from the rest of its siblings and get that close to the host star? It also seems that they are highly inclined relative to their outer planets, meaning that we see a lot of them in single planet systems where there's only the hot super Earth or hot Earth. And because they seem to be more highly inclined, meaning that the orbits don't line up in the same plane quite the same way that they do in the solar system, that might also be a mechanism to produce them, where we see the hot Earth because it's right next to the star, but we don't see the distant planet, the sibling planets, because the inclinations can be fairly large, and it doesn't take a large inclination to make it so that you don't see the transits. So I think really understanding the history of the hot Earths, it's not going to be quite as groundbreaking as the initial hot Jupiter discoveries, but it is there's some branch in the planet formation, there's some decision point in the planet formation process that either planetary systems will produce them or they don't produce them.
Yeah.
And so understanding the conditions that will produce those kinds of hot Earths, I think, is interesting. There has been some work on it, but it hasn't, some of the theoretical work I don't think has treated the observations. It hasn't, the connection between the theory and the observation hasn't been established. I don't think.
I guess it's encouraging just for a listener to hear that, because there are still many problems that we don't fully have answers to. And so that's a nice example of one. So certainly it's not like we're at a point where, when I was studying physics, I always felt I don't want to do I mean, I loved particle physics, studying it, but I always felt like they've discovered everything. Like there's nothing left to do. Like,
Uh-huh.
I think it's easy to get discouraged as a researcher when a field feels wrapped up like that. Even though it can be intellectually fascinating, it's just not something you want to commit your career to. But certainly exoplanets, that's a good example of how there's still lots of stuff out there we need to work on.
Yeah. And there are, like I said, there are people who have worked on it, but I think sometimes what can happen with theory is that you do a theory, you produce a result, and then it's like, okay, here's the result. And then you might have a sentence or two that says, this could be related to something else.
Yeah.
But because it's an extra bit of work that after you've finished with a project, you don't necessarily want to spend more time using the same language or connecting the same observables. Anyway, so I think there's more room in that area.
So let's go back to a little bit of the history of Kepler. So it was originally called FRESIP, right? The mission. There was one point it's called FRESIP.
Frequency of Earth-sized inner planets.
Okay. And Bill Baruch was obviously championing FRESIP, and then it became Kepler.
I think it was actually if I understand, if I recall correctly, it was Carl Sagan who said, you need to change the name.
Yeah. Great advice, because that was not a great name. Not very sticky.
And I should point out,
FRESIP 1b, FRESIP 2b doesn't
yeah. I should point out that I didn't really understand why the Kepler mission was called Kepler until I wrote the book. It was called the Kepler mission because Kepler predicted the transit of Venus.
Oh, okay. I just assumed it was in homage to Kepler's laws, but yeah.
So Kepler predicted the transit of Venus and of Mercury, and then it was discovered and he happened to live at a time when the transit of Venus would happen right away. So he predicted the transit of Venus, and it was like a decade later when it happened. Otherwise, it would have been a century.
Was Eddington a possible name, or was that a European version of the mission?
Well, there's Plato. What was the other?
I thought there was like an Eddington name at some point for one of these missions, but so people rebrand these missions frequently. I guess my real question was, in these early days, in the FRESIP documents, and even there was a press briefing that Bill Baruch led, I think around the time that Kepler launched. And he said in that and in these documents that he expected to find about 50 Earth-sized planets in the habitable zones of their stars, of sun-like stars, which is a big constraint there. And really, when you look back at despite all the successes of Kepler, it didn't deliver anywhere near that. In fact, it's sort of debatable whether it has any true Earth analogs.
Like 10-ish, maybe.
Yeah, I mean, I think
like a true Earth analog. Yeah, that's a different.
If you want like a sun-like
number.
star,
1 year
close
orbit.
to 1 year period and 1 Earth radius, it's pretty hard. I mean, I think the closest is probably Kepler 452b, which we talked about a little bit before we came on the air. But even that one, and many planets of similar periods have been challenged since. So you mentioned in the book how there was this sort of desire to be very conservative almost. Like we don't want to make claims that end up being retracted because that's embarrassing for NASA, it's embarrassing for the mission. And I'm not saying this was embarrassing, but there were certainly planets that have been contested. Mostly these Earth-like planets that have been contested. So what does that, I guess my question is, what does that mean for the legacy of Kepler? Like if its primary objective was to go out and detect the frequency of Earth-like planets, and it comes back with basically nothing in hand, but it delivered all this other amazing stuff that nobody expected it to deliver, how do we make sense of that legacy, and what does this mean when we think about objectives for other missions?
Okay, so there are people who on the Kepler science team who have said, by the standards of what we set out to do, the mission failed. I'm a bit more charitable in terms of you design a mission. Well, let me put it this way. So I didn't see dark energy in my dark energy experiment that I ran at Fermilab. However, I did achieve the design goal of the instrument. So I'm like, if this thing is here, it will do this stuff. And if we have this sensitivity, then we will see the following stuff. This is what we'll get to. And so we achieved the design sensitivity. With Kepler, a lot of the initial estimates for what stars would behave like was based on the sun. Turns out the sun is more quiet than the typical sun-like star. And so there were things that you couldn't know until after you launched the Kepler mission. There were systematic effects from like stellar astrophysics that make it more difficult to find planets that we couldn't have known until after we flew the mission.
That is quite I mean, it's easy to sweep over that quickly, but it is quite a profound point then. The sun is quieter than most sun-like stars. Just that is already interesting.
It's like 50% quieter than the typical sun-like star.
Yeah. So that would mean we are easier to find the Earth around our sun.
And so that alone means that you should only, at best see 2/3 of what you would expect. The Kepler mission did get cut. It did get cut short. It was originally supposed to be 4 years, and then that was modified to 3.5 years in order to save money. And then we wouldn't have been able to go past 4 years anyways because the reaction wheels failed. The two of the 4 reaction wheels failed. So had Kepler been able to, had the entire K2 mission been
Kepler-1, basically.
Basically an extension of the Kepler mission in the Kepler field of view with functioning reaction wheels, then I think we could have kind of beaten down the noise and made the measurement that we expected to do. So I think the main design goal with Kepler was to get 20 parts per million on a star of a given brightness for a 6.5 hour transit duration. So to be able to see variations in the brightness at 20 parts per million. And that it was able to do for most of the chips. There were some where it had extra noise that showed up.
Yeah, I feel like I really want to sit down with like Gibor Basri or someone who is studying the activity of stars from Kepler, because the narrative you've just described, I feel like is the narrative we mostly hear about Kepler, that this was the reason why we couldn't find the Earths, and it's the one I normally, to be honest, recycle. But when you look at the literature, I find it difficult to find a consensus point on that, right?
That's true.
The star people seem to be in disagreement about, there are some people that say, no, the sun is not unusual. That's not true. And it seems like a little bit more nuanced than maybe as simple as we're making.
And there was an argument in the science team even about, so Ron Gilliland was another person who was looking at stellar variability. And so there were people who were saying, we should have known this and we should have known that. To be honest, I didn't really follow those discussions because I was like, hey, this is good enough for me.
Yeah.
And so I know that certainly contributed. It's kind of hard to imagine that it didn't contribute.
Right.
But in terms of we built this instrument, it had a design sensitivity, and by and large, we achieved that design sensitivity.
But it is notoriously difficult. I mean, RV people suffer exactly the same thing. It's notoriously difficult to detect planets that have either a 1-day period from the ground,
or a 365
because that's the rotation
period
of our own planet, so that injects all sorts of trouble, or indeed a 1-year period. I mean, I don't know if you know this story. Famously, the first ever, well, it would have been, but it was retracted. The first ever Nature paper of a exoplanet was the year before Alexander Borshkan's paper, and it was exactly 6-month orbital period pulsar planet. And it was Matt Bales, and I did a video with Matt because I was in such awe of what Matt did. Matt realized there was a mistake in the calculation and that the 6-month period wasn't real. He hadn't corrected for the Earth's eccentricity properly, and that injected this very slight effect, a 6-month spurious signal. And he stood up at a conference and retracted it, and he got a standing ovation for retracting it. And then the next talk after was Alexander Borshkan, who said, "We've got the first." But for real, but he didn't get a standing ovation because I think everyone was like, "Well, this is probably BS."
This should be a lesson to all scientists that if you demonstrate the ethics that go along with like the discoveries and the claims that you make, if you demonstrate the integrity that is expected of us as a profession, you will be respected for it.
Yeah, hugely so.
So you may not get the Nobel Prize, but you will be respected for it.
Yeah. Well, he ended up winning the Shaw Prize for his discoveries in pulsar work later on anyway. So he's done incredibly well for himself. So yeah, I think that's a really important point of integrity. But I guess my original point was just that discovering a 365-day or close to that period is always going to be challenging, because the spacecraft, it's not an orbit of the Earth and it's not an orbit well, it is kind of an orbit of the sun, but it's in this Earth trailing orbit, right? So
Uh-huh.
it does have a
It's
period,
like a 54-week period or something like that.
a 54-week period. Yeah, so it's pretty close to a year then. So it's
Mhm.
therefore, if there's any kind
I
of,
think it's like 370 something days.
well, yeah, any kind of annual cycle on board that spacecraft
Hmm.
will, in some subtle way, pose a risk for fake signals.
Well, and especially because there are periodic noise. There is some chips had periodic noise in it called rolling band, and I'm sure there was other things I didn't really get into detail about. Like I didn't know the nitty gritty details of all of the systematic effects that they had to pull out of the data in order to look for planets in the first place. So when you couple, I have one set of noise that's going to be going at a millihertz or something like that, and you couple that with this periodic, or the 370 something day orbit of the spacecraft, then it's not going to exactly line up with the orbit of the spacecraft, because it'll coincide with some other noise. Like, where does that noise line up in phase with the orbit from the planet? So one of the things that happens in particle physics is, the rule of thumb is that for every order of magnitude in sensitivity that you improve, you're going to run into pi systematic effects. So, for example, if we want to go from, if we want to get to 10 to the minus 32 barns to 10 to the minus 33 barns, or whatever the quantity is that people would look at. So that order of magnitude, now you have to account for the fact that the water that seeps into the ground has there's going to be oxygen at a different level in the history of the Earth. I mean, so there's these kinds of weird things that'll creep in. I mean, I'm just making that one up, but
yeah.
I know, like, for example, the lunar laser ranging, so measuring the orbit, the distance to the moon, they have to worry about the tidal bulge hitting certain continents, and this, like, just the scale of things that that can affect the orbital period. Plate tectonics and volcanic eruptions and things like that show up in the data when you're talking about centimeter measurements.
Yeah.
Probably even just the water soaking into the ground is enough to change.
Yeah, trust me, I'm very aware of that in my long searches for exomoons, of coming across unexpected slight annoyances that can drive you crazy like that. So, but I do think also analogy with exomoons and with Kepler, which obviously there's a strong connection there, but in general, when you set out with an objective, it's cliche, but it's always like the journey that counts in a way, because
It's the friends we made along the way.
yeah, it's along the way, because you really can't anticipate what you're going to find. So with exomoons, we had this project called the Hunter for Exomoons of Kepler, HEK, and we didn't find any exomoons in the Kepler data, but we found the first. Me and David Nesfoni led the paper. You probably know it. Kepler KY 872, Kepler 46. It was the first non-transiting planet for which we were able to get a unique orbit of, because the TTVs were just like astonishingly good for this object, so you could just back out everything. And then there was another one we found, and that was originally, we thought that was an exomoon. At one point we were like, this could be an exomoon. It ended up not being an exomoon, but it ended up being this science paper that we published, and it's very well, high impact work, so you don't expect that, but that's one of the things that falls out the side. And we also had, I think, the first TTV planet that was one Earth mass. It was 1.0 Earth mass. It was the lowest confirmed mass at the time. That was also one of our exomoon false positives. And it's the same with Kepler. Like, you can say, okay, fine, it didn't find its 50 Earths, but it can't control that. Like, you don't know how many Earths are out there until you do the experiment. It has a pretty good upper limit, actually. You actually have some bounds, but you can't control that. But when you build whenever you build an order of magnitude improvement in sensitivity, you see astonishing stuff fall out of the sky, right? You see all sorts of amazing things in nature, and I think this is true of particle detectors as it is for astronomical detectors. That order of magnitude rule seems to work really well.
Yeah, and so in terms of, like, did Kepler meet all of its? Now, Kepler had several science objectives. It wasn't just A to Earth.
Yeah.
A to Earth was one out of 11. It's either 8 or 11. There was some list, and of course it's probably going to be 6, but there's a sizable list of objectives that Kepler had, and so I'm sure it did pretty well on the other ones. To be honest, once the data started coming in and we started seeing, we didn't really even expect these planets to be there. It's like, okay, so there was a particular measurement that we have estimates for it, the estimates, the error bars on the estimates are larger than what we would want. Well, so when Kepler was designed, the solar system was the only thing that we had to go on, because the first exoplanets around a main sequence star wasn't until 1995. Kepler started in 1984. And so the estimates for the number of things that you would find was based on, at the time in the literature, was like the rare Earth idea that, there's only one out of every billion stars is going to have an Earth-like planet in a habitable zone. And something, some small number. I was in middle school at the time, so I don't remember. But the prediction was that there would be none or very few. And then it's like, oh, actually, as we start seeing things, then it's going to be a little bit more. And so then Kepler was built around the idea that we might see a few dozen. It wasn't until, so what Kepler found, when I say like a Kepler planet, a Kepler-like planet, I'm talking about planets that are a couple to 5 Earth radii, and, well, 5 is a bit much, but 2 to 3 Earth radii and 10-day orbital periods. Those ones weren't found until 2000. Kepler was selected in 2001. And so in fact, the first one I think was found around 2000, and it wasn't really until 2007 or so where the Doppler shift surveys were finding enough of these kind of hot Neptune type things to be able to make definitive statements about how common they would be. This was well after Kepler was built, and I think it was right before Kepler launched. I think it was 2007. There was a meeting in Boston where Michel Mayor, and so the Geneva group, Michel Mayor and Didier Queloz, they made the claim that something like 30% of F, G, and K type stars have Neptune, like a planet of some size in less than 50-day orbit or something like that.
It was controversial because I think they never released the data associated with that paper.
This is like that sounds like this. I'm remembering that as you say it. I think that sounds right. So it came out in the proceedings, but that was well after Kepler was selected, and so none of that was predicted. None of that went into the design of the mission. So when Kepler launched and it started finding all these things, it was like, wow, what are we going to do with it? There's so much that we have to learn because these planets are so different than the solar system.
Well, I want to give us a little bit of time to talk about other things apart from Kepler, but we can kind of segue from weird planets a little bit neatly here because you did write an interesting paper that I just want to briefly ask you about that combines your two joys of thinking about particle physics and maybe you've written a few papers like this, but combining particle physics and planets. And you wrote this with Dan Hooper in 2011. So again, the same time as that meeting, I guess. And the title is Dark Matter and the Habitability of Planets. And you kind of argue that it is possible that dark matter could, in some cases, make planets habitable. Do you want to maybe explain this fun idea?
So this paper came out at a time when dark matter discovery was right around the corner. So I was at Fermilab at the time, and there was a wager. So at Fermilab, everything happens at Fermilab. It was the center of the universe for anything related to particle physics because CERN hadn't turned on the LHC yet. That was still a few years away. And so everybody went through Fermilab. Dark matter went through it. Particle physics, there was stuff going on there. And I remember sitting in one of these conferences and there was a wager about how many people think we're going to discover dark matter particles within the next 10 years. And like a third of the people raised their hands. So they lost. But one of the things that was motivating, or one of the signals that you look for with dark matter is if it's certain class of particles, then they can annihilate and produce photons. So they annihilate.
Self-annihilation.
They're their own antiparticle, basically.
So like a photon.
Like a photon, yeah. So you have a dark matter particle hits another dark matter particle. They're their own antiparticles, which is common or not unheard of in particle physics, that a particle is its own antiparticle. Photons is a good example, but it's probably not the only example.
Bosons more generally, or
so with bosons, yes, but you can also have. I'm not going to say that all bosons are like that because I don't think that's true, but certainly with the photon it is. It depends on what other quantum numbers the thing has. Photons are neutral, and so they can be their own antiparticle. But neutrinos might also be their own antiparticle. and that's not yet determined. But I think we're at the place where we should know the answer to that question if neutrinos are their own antiparticles. That is going to be interesting, because if they are their own antiparticles, then that might explain why we exist in the first place, or at least part of why we exist in the first place.
Wait, I can't let that go. What do you mean?
Because in the early universe, you have this hot soup of particles, and basically all standard model, virtually all standard model interactions produce equal numbers of particles and antiparticles. There is, and yet, if that was true, then all of the matter and antimatter would annihilate, and there would be nothing left over but neutral bosons that, like photons. So the fact that we exist and are made out of matter means that there had to be some mechanism to favor producing matter over antimatter. And we don't know we haven't gotten to the bottom of that yet. We have some examples so in order to do that, you have to have what's called CP violation, charge parity violation, that if you switch the electric charges and then you run the experiment in a mirror, like in the mirror universe, the phantom realm where Admiral Zod is located, if you run it in the mirror universe, then you get a different answer. And so we know of a few instances where the CP symmetry is violated, meaning that you don't get the same result if you switch the electric charges and run it in the reflected universe. But it's not enough to explain the matter-antimatter asymmetry, why there's more matter in the universe than antimatter. So if neutrinos are their own antiparticles, then it gives you a way to take antimatter and turn it into matter, or vice versa. And so that might be a way of favoring. That's also
they use
CP
the
violation.
neutrinos as like an intermediate step almost.
Yeah, it's a way of, what it would be is a way of generating like quantum numbers. It's a way of generating electrons, or it's lepton generation, that you're able to produce neutrinos and other particles that couple to neutrinos. So it's a CP violating thing where because the neutrino can become its own antiparticle, you can spontaneously produce particles made out of matter that you wouldn't get. So I don't know all the details of like what is allowed and what isn't allowed. I do know that
sounds like it's a huge deal though if we confirm that. Yeah.
Yeah, if that was so, what they look for in this case is called neutrinoless double beta decay. So this I can say with certainty. It's neutrinoless double beta decay. The idea is that you have a beta decay, which is an electron that gets produced, electron or positron, either one, and then that, in order to produce that, you also have to produce a neutrino or an antineutrino. But then that specific neutrino converts into the other kind, like converts into its antiparticle, and then interacts with the nucleus a second time, the same nucleus a second time, and then produces a second beta particle. So you get two beta emissions with no neutrinos, because the neutrino turns into its antiparticle and then like interacts with the nucleus again.
So does the neutrino have to scatter off something to come back? How does it go back?
It's basically just like that you have this decay that happened. The nucleus has a given size, and so the question is, what's the probability of two neutrino interactions taking place within the size of the nucleus, and within the time frame of the speed of light crossing time? It's probably something like that.
Okay.
So these are I think the experiment that's doing this right now is called Majorana. I don't know if it's been run or not, but that would be a big deal to see that.
So let's try and come back to dark matter. So it's possible there are some flavors of hypothesized dark matter
that are their own antiparticles.
Their own antiparticle, and thus they can produce energy essentially.
Right. So, and there were a lot of people who were looking like in the center of the galaxy to see, is there dark matter annihilation happening in the center of our galaxy or in the center of other galaxies so you annihilate them and then they produce high energy photons. And so do we see excess high energy photons coming from the cores of galaxies?
Could they not just decay? Or they're totally stable? They seem to be.
So with these, it depends on the overarching theory that you're using to generate the particles. So basically, the way that physics works is the universe behaves in a certain way. We have mathematical models that we use to try to map what the universe does to this mathematical language, and so all of these models are basically our way of trying to take what we observe and to map it onto some mathematical structure that we can say, oh, if this is true, then we can make predictions with it using it. We know in the end that all mathematical models are wrong, but some of them are useful. So in this case, the question is, we need to generate a dark matter particle. So what do we need to add? What kind of mathematical structure do we need to add to the existing theory to allow for the presence of this particle that allows it to interact? So you have to have a way of mathematically describing the existence of a field, what the fluctuations of that field look like. So that's a particle, is when you take the electromagnetic field and you wiggle it, you produce photons. Mm-hmm. When you take the neutralino field and you wiggle it, you produce neutralinos, or the gravitinos or smorphinos, or whatever kind of eno the theory produces. So you have a mathematical model. You say it's got this field. That field has certain properties. When you wiggle the field, you get these particles. And then you say, okay, given what this model has, the way this model behaves, what kind of decays are allowed to happen, like what kind of interactions are allowed to happen, and which ones are forbidden. And it turns out that with most of them, with most of the dark matter candidates that at least existed up to this point, dark matters, we haven't seen any of them, so the evidence for them is basically zero. The evidence for specific particles is basically zero. The evidence for dark matter is compelling, but we don't know what it is. At the time, there were a lot of these particles that were theorized, and within that theory, you would have a stable particle at the bottom of the allowed hierarchy. It's basically like saying there are three versions of the electron, and there's the super duper heavy version of the electron, there's the intermediate version of the electron, and then there's the lightest version of the electron. The heavier ones are unstable, and the lightest one is stable. And so it's kind of the same idea, where you could have this type of particle. It might have a tower or like a hierarchy of similar particles, but there's going to be a lightest one, and that lightest one you can't get rid of because there's no mechanism to get rid of it in the mathematical model. Now, the universe doesn't have to behave, doesn't have to follow these mathematics, but the mathematics is what gives you the predictive power.
Right.
So the idea was that you then have these particles, they could annihilate with themselves, generate a bunch of energy. And if they can generate energy, then they can warm things up. And in particular, they're going to warm things up because the dark matter is going to be concentrated in the center of dense regions. So it'll be concentrated in the center of the sun and in the center of planets. So in this, what we were looking at for this paper was, if these dark matter particles exist and they're still allowed based on exclusions from searches for them. So the particles exist, they might be right on the verge of being discovered, and they collect inside of planets because planets are a dense region and gravity is going to cause them to coalesce into that area. And then they start annihilating. Now you're depositing a bunch of energy into the core of a planet, and that energy can make it up to the surface and raise the temperature of the surface up to the point where you can get liquid water on it, even if the planet doesn't have a host star nearby to provide any external energy. We see this in the Earth, right? The Earth has nuclear decays happening in the core of the Earth that keeps the Earth's core molten. If it wasn't for the uranium and thorium in the core of the Earth, then we might not have a liquid outer core, which means we wouldn't have a magnetic field, which means we wouldn't have a number of other things.
So if this was true, wouldn't therefore the amount of dark matter in the universe be decreasing over time?
Yeah. So it's the interaction cross-section would be very small, but not zero. And so over time, the dark matter would eventually dissipate.
Which sounds like it has some cosmological implications in terms of both the fate of the universe and the early universe, potentially. Mm-hmm.
So it probably doesn't affect too much, because you first have to grow the structures before you can, like the dark matter is going to be spread out first, and then you have to concentrate it in order to get a high collision rate, like a high annihilation rate. And then the question is, how long do you have before you run out of dark matter in a galaxy? And the answer to that question with these interaction probabilities is like you have 1 billion times the age of the universe. It's some huge number. And so while it does decrease over time, it decreases at a rate that's kind of slow. I mean, I do this calculation with middle school students in in the camps that I run, where I say, the sun is losing mass every day. Is it going to be there tomorrow? How do you know it's going to be there tomorrow? We should find out how long is the sun going to survive, given the fact that it loses like a billion kilograms of matter
Yeah,
every
it's
second.
like a million tons or something, right? And you think that sounds horrendous, but then when you actually do the math, it's a drop in the
Yeah, so
ocean.
you add up,
Yeah.
okay, here's the mass of the sun, and
Yeah.
here's how much mass it's losing every second.
Yeah.
And it's like, oh, okay, we got 10 billion years. So,
Right.
so we're good. It'll be there tomorrow.
Yeah, yeah.
And so it's kind of the same idea where there is annihilation. We would be losing dark matter, but the rate that we're losing it is so small that it's not going to affect anything that would matter to us.
So there's a good example of what I mentioned earlier, that you have this wonderful mind where you love to explore different aspects of planets, different aspects of physics, and probably the most extreme example I've encountered with your work, and I know you kind of had a little side career from it for a little bit, was boarding planes. So you can tell our listeners what is the best way to board an airplane and why. How do you know that?
Okay. So not the way that it's done. So the best way, the fastest way to get passengers onto an airplane is not to do it filling from the back to the front. That was what I thought going in when I was like, this seems like a solvable problem. Well, a little bit of background. So I went to the airport and I was in traffic, which is annoying enough. And then I'm waiting at the security gate, which is also annoying. And then after the security gate, I'm waiting to scan my ticket at the kiosk that's outside of the gate. And that was annoying. And then after you scan your ticket, you go into the jetway and you're standing in line again. And that was enough. I'm like, if this was more efficient, then waiting in line to check my ticket should be all that it takes. And then there's no other waiting. I just go straight to my seat if it was more efficient. So obviously there's some kind of inefficiency in here. And I thought about it for a long time, thinking about how am I going to do this? And it turns out that I probably thought about it way more than I needed to, because I was anticipating that if I were to actually solve the problem, like build a model for how to move passengers in the airplane and solve it, that it would take me a long time to put the code together, but it actually only took me like an afternoon to write it. So that was a lesson learned. Like if you have some idea and it's kind of gnawing at you, just do it. But
then I guess you were making like the spherical cows type approximations, right? You can't.
Yeah, there were some approximations that went into it. But that's the nature of doing physics theory is like, let's start with some approximations and we'll see what we can get to first order.
Yeah.
So I thought going in, boarding from the back to the front was obviously the fastest because you just get people in, no one bumps into each other, everybody's out of the way, and you just file in and sit down. And so I ran the code boarding from back to front, and I was like, okay.
So people can't pass.
There's no passing. You just like, what I would do is I would just line the passengers up, and then I would say go, and then they would move down the airplane and sit down.
And then some of them just hang. Do they hang whilst they're putting their baggage up, or do they just
sit so I
down?
had how much time do they have to store their luggage, and that was an adjustable parameter.
Okay.
How fast do they walk? I mean, I basically just said a row is a step, and so I did just tiny steps like that. It was a really simplified model. And then I thought, okay, so if that's the best case scenario, then the worst case scenario is obviously going to be going from the front to the back. So I'll just reverse the order and send it in. And then that will give me the whole spread of what's the best to worst. And I got basically the same answer. And I was like, this can't possibly be right. I got the same answer going front to back as back to front. Something's got to be wrong here. And so maybe I wrote the code wrong. And so then I built this animation, which was basically I just had it print out a text file of a bunch of exclamation points marching across the screen. And I was like, it's behaving the way that I think it should, where if someone stops, then everybody stops behind them. And then when they start moving, a gap opens up and then the next person, so it like accordions in and out as the line moves. And I was like, yeah, that's the behavior of a line. So I got that right. So what's going on? So then I decided to do random switches of passengers and see if it gets faster. So it's the Markov chain Monte Carlo, the traveling salesman version, where you just switch a couple passengers around, see if it goes faster. If it goes faster, you keep the change and you switch two other ones and you keep doing that over and over and over again. Eventually you converge to the optimum. It turns out the problem with boarding back to the front is that you have 6 people that are all trying to get into the same row. And so you have to wait for one person to put their luggage away and sit down in order for the next person to get to that row and put their luggage away and sit down in order for the next person to get to the row. And so you're waiting for 6 people to fill one row.
Right.
You're not using the aisle at all. And the fastest way to do it is to spread passengers out in the aisle. So you have as many people in the airplane as possible who can simultaneously put their luggage away without getting in each other's way.
So you want to distribute them almost uniformly.
Yeah, you want to spread them out as much as possible in there. In the aisle, so that instead of having one person putting their luggage away at a time, you can have 10 or 15 or 20 put away their luggage at the same time. And if you do that, then you've taken a serial process and turned it into a parallel process where everyone puts it away, and then you send it another group, then they'll put their luggage away, you send it another group. So I estimated that it would be basically one extra row of space. That might be overkill, but that was, what if you need 2 rows of space? What if you need 5 rows of space? The answer is you spread them apart, whatever the minimum number of rows people need to put their luggage
So
away.
you just do the odds and the evens then?
Yeah, so you'd send in basically every even row, the window seat on one side. So every even row, in order, back to front, send it in, and then everyone can put their luggage away at once. And then you send in the middle seat and the window seat, then you go to the other side and you do the same thing.
Yeah.
So it would take 12 groups arranged the right way. So the first question that people ask is, no one's ever going to do this. Like, why?
Yeah, because people want that prestige level of boarding
and how are you going to get people to line up this way? How are you going to force people to do this? Now that was actually solved by Southwest Airlines at the same time, because that's when they did their bordered, their numbered key or like pylons that you'd stand by.
Yeah.
But the real answer to that question was, it doesn't matter if you can implement it. The physicist in me is like, the implementation is not the issue. It's what is the optimum. What you do doesn't have to be the real optimum, but you want to understand why the optimum is the way that it is. And the optimum is that you use the aisle as much as possible. You have people spread out all throughout the airplane to put their luggage away all at the same time. And you arrange them so that they don't interfere with each other trying to get past to go to the end of the airplane. And when you do that, that's what makes the boarding process the fastest.
So did you consult for an airline or anything to help them?
There were a couple that reached out to me, but then nothing ever came of it. Now I will say, even though I was there's the Steffen method. It was named. I called it the Steffen method in the second paper that I wrote, because I was like, well, what are we going to call it? I got to call it something. But there was a paper that came out before mine that actually had the same answer, and they blew it off.
What do you mean?
They had this result. It showed up. It was like way faster than they tested, like 50 different ways of boarding airplane passengers. I'm going to block it up like this. I'm going to send them in windows first, then middle aisle. I'm going to do like random number generator. They had a whole bunch of different things, including every other row, this person, and it was way faster. I mean, it showed up in their data that they have a graph, and there was a big dip in the boarding time on that one thing, and they blew it off because it wasn't practical. And it got like a half a sentence statement about that thing. And I didn't know about that until after I did my paper. And then I was like, oh, look, they had it. It's right here.
Yeah. Did they write to you and complain then?
No, I don't think that. I think it was just like they did the paper and it was kind of the one-off thing. And then the guy, whoever it was, graduated or whatever. But to me, it just drives home the point that if you see something interesting, you should follow up with it. I mean, there's a really good example in exoplanets. I'm grateful that, so the Radius Valley that exists, I saw it. I even had a sentence in one of my papers like, oh, this looks like a thing. I remember spending a couple of weeks trying
This is a paucity of planets at around about
like 1.5 Earth radii. Yeah. I saw it in the paper that came out in 2016 that I wrote with Jeff Coughlin. Like it looked like, I'm like, this looks like bimodal. How do I see if it's actually bimodal or not? And I fiddled around with it for a couple weeks, and then I was like, I'll just take that sentence out and won't worry about it. And then a year later, the California Planet Survey is like, look, there's this bimodal thing. It's got like 1,000 citations. And
could have been the Steffen gap.
Well, I mean, yeah, it could have been. My TTVs, I'm not worried about my career in terms of that. I'm grateful I'm happy for them to do it because they did a lot of work. Because one of the things that really brought out the gap was the fact that they had better measurements of the stars, and that didn't exist in the data that I was analyzing. So their signal is way beyond what I was able to do, would have been able to do, and so. But what if nobody had said anything for a decade? So there's 1,000 papers that have been written on that they happen to be looking at it as well. And the fact that I blew it off, that to my everlasting shame, that could have been something that set things back.
Yeah.
So I always tell my graduate students, if you see something interesting, don't blow it off.
Yeah.
Figure out what's going on in that interesting thing, because this other paper that did the airplane boarding thing, they had the answer. It was right there.
Right.
And it was anomalous. It was way faster than anything else that they looked at. And they did the same thing that I did. It's like, I'll just, some other time.
Yeah, well, I think there's a lot of wisdom in that so often it might feel easier to blow it off because you don't want to have to do the intellectual effort of trying to explain
You just want to
it,
get the paper out. You've been working on it forever.
Right. You've got a deadline and you just do that. So, but often you can overlook how many amazing discoveries might be sat in our data already that people have blown off that same way. So keep our eyes open. Jason, we've covered a lot of ground here today. Thank you so much for your time. And I want to just really point people towards this book, Hidden in the Heavens, by Jason Steffen, available online on all the bookstores. Really enjoyed this book. If you want to hear more about the history of Kepler, where else can people find you?
Well, so I'll probably disappoint them if they follow me on Twitter, but I'm Horizon Sci on Twitter. But I have, I'm a physics professor at UNLV, and that's probably
the best place to find you. Okay. All right. Thank you again, Jason. It's a great pleasure. Thank you.
My pleasure. It's good to talk to you.
So that was my conversation with the wonderful Jason Steffen, an old friend and colleague, a professor of physics at the University of Nevada, and the author of this book, which I encourage you to check out, Hidden in the Heavens, which really chronicles the story of this Kepler mission. This mission which was possibly one of the most transformative experiments ever done in human history. I don't think that's actually an exaggeration to say that, given how profoundly it shifted our understanding of planets in the universe. A question which, let's face it, we have been wondering about as a civilization for thousands of years. So a profound story. Please do check that out. I just want to finish by reflecting a little bit on the Kepler mission. It was a highly impactful mission to my own career and to Jason's. Obviously, we kind of we cut our teeth on that mission, and so did many others. Hundreds of scientists, in fact, were trained and built up their expertise from that mission. And perhaps that is the greatest product of the whole mission, is all these people out there who've now got professorships and postdocs or whatever in their future careers, and they are then using that expertise to train the next generation of scientists and keeping this ball rolling of expertise. So if nothing else, just the human side of things is a huge success for Kepler. But the scientific legacy is interesting as well, I think. I think it would be a little bit cheap and unfair to say that Kepler did not deliver on one of its primary mission objectives. It is factually kind of true, but it also kind of undershoots a little bit, and it kind of misses the mark of all the other stuff that Kepler did. So the primary objective, as we mentioned in the podcast, was to try and detect Earth-like planets. And they were talking about numbers of like dozens, like 50 Earth-like planets that it would find. And by Earth-like, we really mean same size of the Earth, same kind of distance away from the sun that the Earth is, and orbiting a sun-like star. And it just didn't find really anything convincing in that area, in that ballpark. Found some things that were pretty close, but not quite that. So that is maybe a disappointment to some of us. I think that's what we all hoped, that it would find those worlds. But it has taught us so much that we didn't anticipate. So, for instance, the discovery of mini Neptunes. These are the most common type of planet in the whole universe. And that is something we had no idea about until Kepler came around. The discovery of circumbinary planets orbiting two stars, like the kind of Tatooine type situation you have in Star Wars. I mean, that was kind of sci-fi until Kepler came along and proved that there's actually lots of those things out there. Transit timing variations, wobbling worlds. That was something that we were trying to do from the ground with ground-based telescopes for years, even a decade at least, before Kepler launched. And time after time, it was just not working. We just couldn't get convincing results. And then Kepler just found dozens and dozens of these really high signal-to-noise detections. So another huge win for Kepler. And then just, the wild diversity of exoplanets that it unleashed upon us. Everything from M dwarfs, K dwarfs, sun-like stars, F dwarfs, even giant stars, seismology, transients. It was a rich zoo of discoveries that we really couldn't keep up with. It was kind of like drinking from the fire hose, as Jason said in the podcast. We just couldn't keep up with the rate of discovery. And I think that is the greatest scientific return that we got from Kepler, all those things that we didn't expect. And I would argue that for a lot of missions, for a lot of experiments, that is often the way it is. It's not always true, but often it is true. Whenever you build an experiment that is, let's say, half an order of magnitude more sensitive than anything that's come before, so that's like a factor of 3, roughly. An order of magnitude is a factor of 10, half an order of magnitude is a factor of 3. Whenever you get to that kind of 3x improvement in sensitivity, you can guess what you're going to find, and you can have a noble goal as to what you want to find, but you really don't know what you're going to find until you do the experiment. And as Kepler demonstrated, and many of the experiments have demonstrated, what you find often surprises you, and surprises you in a good way, right? It can either be the lack of the signal that you expected, which is kind of true in the case of Kepler looking for Earths, but also all of these surprising positives that nobody really thought would be out there. I think hot Jupiters is perhaps the most classic example of that. Who expected planets to be orbiting so close to their star as hot Jupiters are? That was one or two people did, but the vast majority of people did not expect that. And so it was an extremely transformative discovery. It kind of shifted the whole trajectory of the field of exoplanets after that point. And so what I hope the legacy of this little telescope is, little, it was a meter across, to be fair, it's not that little, but of this, small compared to James Webb telescope, is you have to try. You have to put yourself out there. You have to build these missions. And when you do that, if you push the envelope, you push the sensitivity, you deliver the precision, the science will follow. Just trust the science will follow. Whenever you access the universe at a greater level of sensitivity than you've had before, wonderful stuff will fall out. I think that's the story of astronomy for sure, and the story of many of the fields of science. So to me, that's the greatest legacy of Kepler, is not only the human training of all these wonderful scientists, but just the idea of just listening, hearing, seeing, and seeing all this wonderful science just fall out of the sky into your lap, stuff that you can't anticipate. So yes, we should still write our proposals. Yes, we should still try to predict what we're going to find, but we should always take those proposals with a huge grain of salt. If the mission is going to deliver that sensitivity increase and you feel confident about that, let's do it, because it's going to discover cool stuff. That's enough for me. So I hope that's a good lesson from this mission and for other experiments as well. And it gives me a lot of hope for the future. So if you're enjoying these kind of conversations, these chats that we're having on the podcast and the other stuff we do on the YouTube channel and the Cool Worlds main channel as well, and you're thinking, how can I support what they're doing over there in a meaningful way? Of course, you can do all the usual YouTube stuff. You can add this to your Spotify lists. You can bookmark this. You can like this. You can share this. All that kind of stuff helps us. Please do it. I don't want to underscore and undersell that. I don't want to say don't do that. Please do that. But if you have the financial capability and the interest in supporting us, you think we deserve it, then honestly, the best way to support us is, for the price of a coffee per month, like $5 per month, you can support our channel. You can support this podcast by heading to coolworldslab.com/support. That's coolworldslab.com/support. And now you can become a member of the channel. You get access to all kinds of special perks depending on what membership level you hit. And that way you're supporting real research, the real research at the Cool Worlds Lab. And by supporting that research, it means I have to spend less time writing those annoying grant proposals, and it means I can be supported by you guys directly, which gives me more time to make these podcasts and episodes on the main channel. So that's honestly the best thing to do. So please do check that out if you're interested. Link down below in the show notes. And as always, it's a pleasure to see you all, and I will see you next time. So please stay thoughtful and stay curious.